They say the ground doesn't lie, but what if the animals knew first? What if, hidden beneath fur and feathers, within hooves and fins, there exists a network of senses so refined, so ancient, that they can read the Earth's whispers, hours, sometimes days, before disaster arrives? Tonight, we step into that invisible world. Welcome to Bedtime Biology, where science meets serenity. Each night, we explore the quiet wonders of the natural world, calming your mind and sparking your curiosity. If you like these videos, please consider subscribing to the channel and commenting below if you have any feedback or suggestions for topics of future episodes. The world beneath our feet is never truly still. Deep within the Earth's crust, tectonic plates shift and grind against one another with unfathomable force. Storms gather over warm oceans, drawing energy from the water below. These are the planet's rhythms, powerful and ancient, yet most of us remain unaware until the moment they make themselves known, when the ground begins to shake, or the sky turns dark with fury. But what if I told you that all around us, countless creatures have been listening, feeling, sensing these changes long before we ever could? What if the natural world has been speaking a language we've only just begun to understand? For thousands of years, humans have told stories of animals behaving strangely before earthquakes. Dogs barking at nothing, cattle refusing to enter their barns, snakes emerging from winter burrows weeks too early, slithering across frozen ground as if fleeing from some invisible threat. Birds taking flight in the dead of night, their wings beating against the darkness in patterns that make no sense. These accounts span cultures and continents, from ancient Greece to modern China, from the shores of Indonesia to the plains of North America. For much of history, such tales were dismissed as folklore, the product of frightened minds seeking patterns in chaos, trying to make sense of the senseless violence of natural disasters. But in recent decades, something has changed. Scientists armed with accelerometers, GPS trackers, and sophisticated monitoring equipment have begun to document what our ancestors observed with nothing but their eyes. They've watched elephants flee coastlines hours before tsunamis struck. They've recorded farm animals growing restless a full day before the earth began to shake. They've tracked sharks swimming to deeper water as hurricanes formed hundreds of miles away, and observed birds altering their migration routes in response to barometric pressure changes invisible to human perception. What emerges from this research is not a simple story of animal precognition or mystical sixth senses, but something far more fascinating, a testament to the incredible sensory adaptations that evolution has refined over millions of years. The question isn't whether animals can detect earthquakes and storms. The evidence increasingly suggests that many can. The real questions run deeper. What exactly are they sensing? How do their bodies translate subtle environmental changes into actionable information? And perhaps most intriguingly, can we learn to read the same signals, to tap into this ancient network of natural warnings that has existed far longer than human civilization itself? Tonight, we're going to explore these questions together. We'll journey from the molecular vibrations that ripple through rock to the pressure waves that sweep across oceans. We'll discover how a dog's inner ear might function as a biological seismograph, how elephants can hear thunderstorms from 100 miles away, and why sharks possess what amounts to a living barometer embedded in their bodies. We'll examine the scientific evidence, both compelling and contentious, and we'll meet the researchers who are working to separate genuine animal sensitivity from coincidence and confirmation bias. This is a story about survival, about the relentless pressure of natural selection that has shaped creatures capable of reading the Earth itself. It's about the hidden channels of information that flow through the natural world, channels that we're only now learning to detect with our instruments, but that animals have accessed all along. And it's about the humbling realization that for all our technological advancement, there are still things that a simple farm animal can sense better than our most sophisticated equipment. So, settle in, breathe slowly. Let your mind drift into this exploration of one of nature's most mysterious phenomena. Because tonight, we're going to learn to see the world as the animals do. A world where the air itself carries warnings, where the ground speaks in frequencies too low for human ears, where the approaching storm announces itself not through clouds on the horizon, but through the invisible language of pressure and vibration. We're going to discover that the animals aren't predicting the future at all. They're simply paying attention in ways we've forgotten how to do. The story begins, as so many scientific inquiries do, with an earthquake and a mystery. But before we can understand what the animals know, we need to understand what an earthquake is. Not as a human experiences it, but as a physical phenomenon that radiates through the earth in waves we can barely perceive. We need to understand the invisible architecture of disaster, the precursors and signals that our instruments can only just detect, and that animals may have been reading for eons. Let's start with the science of shaking ground and the remarkable discovery of what animals might be sensing in those crucial moments before the world begins to move. When an earthquake occurs deep beneath the surface, it doesn't simply make the ground shake. What we experience as a single terrifying event is actually a complex symphony of different types of waves, each traveling at different speeds and carrying different types of energy through the rock. Understanding these waves is crucial to understanding what animals might be detecting, because not all earthquake waves are created equal, and not all of them are equally obvious to human senses. The first waves to arrive are called primary waves, or P waves, sometimes known as compressional waves. These waves travel through the Earth at remarkable speeds, typically 5 to 8 kilometers per second, depending on the rock type they're passing through. P waves are special because they can travel through any material, solid rock, molten magma, water, even air. They move by compressing and expanding the material they pass through, like an invisible accordion being played through the substance of the Earth itself. When a P wave passes through rock, it momentarily squeezes it together, and then allows it to expand, creating a rhythmic pulse that races ahead of everything else the earthquake produces. For most humans, P waves are completely imperceptible. They're too subtle, too brief, too easy for our senses to miss in the constant background noise of modern life. A seismograph will record them with perfect clarity, marking the precise moment when the P wave arrives with a characteristic sharp spike on the readout. But a person standing on the surface usually notices nothing at all. There might be the faintest sensation if you're very still and very attentive, a barely perceptible tremor, gone almost before you can register that it happened. Most people never feel the P wave at all. They remain unaware until seconds, or sometimes minutes later, when the next set of waves arrives. These are the secondary waves, or S waves, sometimes called shear waves. S waves travel more slowly than P waves, typically 3 to 4 kilometers per second, about 60% of the P wave's velocity. But what S waves lack in speed, they make up for in power. These are the waves that do most of the actual damage during an earthquake. S waves move through rock in a side-to-side motion, perpendicular to their direction of travel, like shaking a rope. They can only travel through solid materials, which is why seismologists can use the absence of S waves on the far side of the Earth to confirm that our planet's outer core is liquid. When S waves reach the surface, they create the rolling, shaking motion that topples buildings, cracks roads, and sends people stumbling for doorways. The time difference between the arrival of the P wave and the S wave depends on how far you are from the earthquake's epicenter. If you're very close, the gap might be only a second or two. If you're hundreds of kilometers away, the P wave might arrive a full minute or more before the damaging S waves reach you. This is the principle behind earthquake early warning systems, computer systems that detect the P wave arrival, rapidly calculate the earthquake's location and magnitude, and issue warnings before the S waves arrive. In Japan, which has invested heavily in such systems, trains can automatically brake. Elevators can return to the nearest floor and open their doors. And surgeons can be alerted to pause delicate operations, all in the precious seconds between P wave and S wave arrival. But here's where the story becomes truly fascinating. While humans typically cannot feel the P wave, many animals apparently can. This isn't mysticism or folklore. It's a straightforward consequence of sensory biology. Animals possess organs and nervous systems tuned to different frequencies and intensities than ours. A dog's hearing extends into ultrasonic ranges we cannot perceive. A cat's whiskers detect air currents too subtle for our skin to register. An elephant's feet are connected to mechanoreceptors so sensitive they can detect another elephant's footsteps from kilometers away through the ground. The P wave might be imperceptible to a human standing casually on the street, but to an animal with the right sensory apparatus, it could be as obvious as a shout. This creates a window of opportunity. An animal that can detect the P wave gets advanced warning of the S wave's arrival. Even if that warning is only a few seconds, it might be enough. Enough time to bolt from an unstable structure before it collapses. Enough time to move away from a cliff face before rocks begin to fall. Enough time to seek open ground before the trees start swaying. From an evolutionary perspective, the advantage is clear. Any mutation that helps an animal detect and respond to P waves provides a survival benefit in earthquake-prone regions. Over thousands of generations, natural selection would favor individuals with this ability, gradually refining the sensitivity until it becomes a reliable early warning system. The scientific evidence for P wave detection comes from multiple sources. During the 2011 earthquake that struck near Washington, D.C., zookeepers at the Smithsonian's National Zoo reported that several species of animals began behaving unusually in the minutes and even seconds before staff felt the ground shake. Lemurs, which are usually relatively quiet during the day, began vocalizing loudly about 15 minutes before the earthquake. The zoo's red-ruffed lemurs, in particular, made alarm calls that are typically reserved for predators or other immediate threats. The timing is significant because 15 minutes far exceeds the gap between P wave and S wave arrival for that earthquake's magnitude and distance. This suggests that either the lemurs were responding to some even earlier precursor, or that the event involved foreshocks too small for humans to notice, but detectable to animals with more sensitive vibration detection. Apes at the same zoo reportedly climbed to the tops of trees in the seconds before the main shaking began. This behavior, climbing to high points, might seem counterintuitive. After all, being at the top of a swaying tree during an earthquake sounds dangerous. But it makes more sense when you consider that apes are adapted to forest environments where the ground itself can be treacherous, prone to landslides and sinkholes. In their native habitat, being in a flexible tree might actually be safer than being on unstable ground. The key point is that the apes were reacting before the earthquake was obvious to humans, suggesting they detected either the P wave or some other precursor signal. But the evidence for P wave detection extends well beyond a single earthquake at a single zoo. Researchers have documented similar patterns in numerous locations. Studies of pets during earthquakes frequently note dogs barking urgently in the seconds before their owners feel anything, cats suddenly fleeing to hiding spots, birds in cages becoming agitated and fluttering their wings. These behaviors occur consistently enough that they can't be dismissed as pure coincidence or selective memory. In 2003, researchers in Germany conducted an elegant study on redwood ants living along a known fault line. They set up cameras to record the ants' activity patterns over an extended period, capturing both normal behavior and behavior during seismic events. What they found was striking. Before earthquakes occurred, the ants altered their usual routines. They became more active at night, when they would normally be resting, and less active during the day, when they would normally be foraging. The change in behavior began hours before the earthquake struck, far too early to be explained by P-wave detection. This suggests the ants were responding to some other precursor, some change in their environment that occurred in the build-up to the seismic event. The most comprehensive modern study on animals detecting earthquakes comes from the Max Planck Institute for Animal Behavior in Germany. Researchers there worked with farmers in northern Italy, a seismically active region that experiences frequent earthquakes. They attached motion sensors to the collars of 6 cows, 5 sheep, and 2 dogs, animals that had previously been observed behaving unusually before earthquakes. These weren't fancy laboratory animals. They were working farm animals living their normal lives, but equipped with what amounted to tiny accelerometers that recorded their every movement continuously for several months. During the study period, approximately 18,000 earthquakes occurred in the region. Most were too small for humans to feel. Tiny tremors that registered on seismographs, but caused no perceptible shaking. But 12 of these earthquakes were magnitude 4 or higher on the Richter scale, strong enough to be distinctly felt and, in some cases, to cause minor damage. The researchers focused their analysis on this subset of stronger earthquakes, looking for patterns in the animals' movement that preceded the events. What they discovered was both fascinating and frustratingly complex. The animals did show increased activity before the earthquakes. In the hours leading up to seismic events, the cows, sheep, and dogs moved more than they did during equivalent time periods on days when no earthquake occurred. The activity increase wasn't random. It correlated with the earthquake's strength and the animals' distance from the epicenter. Animals that were closer to where the earthquake would originate showed increased activity earlier than animals that were farther away. This creates a pattern consistent with the animals detecting some signal that diffused outward from the developing fault rupture. The timescale was remarkable. The unusual behavior began as much as 20 hours before some earthquakes. 20 hours is far too long to be explained by P-wave detection. The P-wave arrives seconds before the earthquake, not hours. This means the animals were responding to something else entirely, some change in their environment that began long before the actual rupture occurred. The researchers were careful to control for other variables that might cause increased movement, changes in weather, feeding schedules, the presence of humans or other animals. The pattern held even when these factors were accounted for. Something about the approaching earthquake was detectable to the animals, but here's where the science becomes uncertain and honest. Scientists must acknowledge uncertainty rather than pretending to know what they don't. The researchers don't actually know what the animals were detecting. They have hypotheses, educated guesses based on what we know about earthquake physics and animal physiology. The most commonly proposed mechanisms involve things that do change before earthquakes: ground tilt, changes in the electrical field, variations in groundwater chemistry, release of radon gas or other volatile compounds from the ground, changes in atmospheric ions, variations in the local magnetic field. All of these have been measured before earthquakes by sensitive instruments. Any of them could potentially be detected by animal sense organs. Ground tilt is particularly interesting. As stress builds along a fault line before it ruptures, the ground on either side of the fault deforms slightly, tilting in measurable ways. The tilt is incredibly subtle, fractions of a degree, far too small for humans to perceive. But many animals have exquisitely sensitive balance systems. Birds have their inner ear structures. Mammals have their vestibular systems. These organs can detect tilts of less than a degree with ease because they evolved to help animals navigate complex three-dimensional environments. An elephant needs to know whether the ground beneath its feet is stable or sloping. A cat needs to land on its feet when it falls. These requirements have shaped balance systems far more sensitive than what humans possess. It's plausible that such systems could detect the minute ground tilt that precedes earthquakes. The electromagnetic field hypothesis is more controversial. The Earth has a natural magnetic field generated by the motion of molten iron in its outer core. This field is relatively stable on human timescales, but it does vary slightly, and some research suggests these variations become more pronounced before earthquakes. The mechanism isn't fully understood, but it likely involves the movement and fracturing of rocks along fault lines, which can generate piezoelectric effects, small electrical currents created by mechanical stress on certain types of crystals. These currents could theoretically disturb the local electromagnetic environment. Many animals can detect magnetic fields. This is well established. Birds use magnetoreception to navigate during migration. Sea turtles use it to find their way across oceans. Sharks have specialized organs called ampullae of Lorenzini that detect electrical fields in the water, which they use to find prey. Even mammals show magnetic sensitivity. Cows and deer tend to align themselves along magnetic north-south axes when grazing, for reasons that aren't entirely clear. If animals can detect the Earth's magnetic field under normal conditions, it stands to reason they might notice when it fluctuates before an earthquake. The chemistry hypothesis proposes that earthquakes are preceded by the release of gases or changes in groundwater composition. As rocks deep underground experience stress, microscopic cracks form. These cracks allow gases trapped in the rock to escape toward the surface. Gases like radon, carbon dioxide, or even methane. Some of these gases have distinct odors that animals with sensitive noses could detect. Dogs, famously, can smell things humans cannot begin to perceive. They can detect cancer in human breath, find corpses buried under avalanches, track individual people's scent trails hours after the person has passed. If earthquake precursor gases exist and have any odor at all, even one we cannot smell, it's plausible that dogs and other animals with acute olfaction could detect them. Groundwater can also change chemically before earthquakes. The same processes that release gases can alter the mineral content of water in wells and aquifers. Studies have documented changes in radon content, pH levels, and concentrations of various ions in groundwater before seismic events. Animals that drink from streams or ponds might taste these changes, especially animals like cattle that consume large volumes of water. Even humans with particularly sensitive taste buds sometimes report that water tastes different before an earthquake, though such reports are anecdotal and difficult to verify. The honest answer is that we don't know for certain what animals detect. We know that something changes before earthquakes. We know that animals respond to those changes, but the causal chain, the exact physical signal, and the exact sensory mechanism remains elusive. This is frustrating for scientists who like clean answers and clear mechanisms. But it's also what makes the research exciting. We're at the frontier of understanding, exploring a phenomenon that humans have observed for millennia, but only recently begun to study rigorously. History is full of earthquake stories where animals seemed to know in advance. The earliest documented account comes from ancient Greece, from the city of Helic in 373 BC. According to the Roman historian Aelian, writing centuries after the event, but presumably drawing on earlier Greek sources, rats, weasels, snakes, centipedes, and beetles all left the city days before a massive earthquake destroyed it. The city was subsequently swallowed by the sea, creating a lasting mystery and a potent symbol of nature's power. Whether the story of the fleeing animals is accurate, we can never know. It might be embellishment, the human tendency to shape narratives around dramatic events. But the persistence of the account, told and retold for centuries, suggests it captured something that people believed or had experienced. Fast forward to 1975, to the Chinese city of Haicheng. This is perhaps the most famous case of animals apparently predicting an earthquake. And unlike ancient accounts, it's thoroughly documented. In the weeks and months before the earthquake, authorities received numerous reports of unusual animal behavior. Snakes emerged from their burrows in midwinter, when they should have been hibernating, and crawled across snow-covered ground. Many died from the cold, but they kept emerging, as if fleeing something underground. Rats acted strangely, appearing disoriented or drunk, wandering aimlessly in public. Chickens refused to enter their coops at night. Horses and cattle became agitated without apparent cause. Chinese authorities in the 1970s were actively studying earthquake prediction, investing significant resources into seismological research. When these animal reports began arriving, officials took them seriously. They also had other data. Seismographs were recording swarms of small foreshocks, tiny earthquakes that sometimes precede larger events. Groundwater levels were changing. The ground itself was tilting, measurable by instruments. All of these signs, combined with the animal behavior reports, led officials to make an extraordinary decision. On February 4th, they ordered the evacuation of Haicheng. Later that same day, a magnitude 7.3 earthquake struck the city, destroying 90% of its buildings. Because of the evacuation, thousands of lives were saved. Estimates suggest that without the warning, 90,000 people would have died. The Haicheng evacuation is often cited as proof that animals can predict earthquakes and that humans should pay attention to such predictions. But the story is more complicated. The evacuation was based primarily on the foreshock activity and the instrumental measurements, not solely on animal behavior. The animal reports were one piece of evidence among many. Moreover, the success at Haicheng has proven difficult to replicate. Chinese authorities have since issued earthquake warnings based on animal behavior that turned out to be false alarms. They've also failed to predict major earthquakes, despite having extensive monitoring systems. The Tangshan earthquake in 1976, just a year after Haicheng, killed over 200,000 people with no advance warning, despite occurring in a country actively looking for precursor signs. This is the central challenge with using animals as earthquake predictors. Even if animals can detect precursors, those precursors don't always occur. Or they occur, but no earthquake follows. The relationship between the precursor signals and the actual earthquake is probabilistic, not deterministic. You can have all the signs and no earthquake, or you can have a major earthquake with no obvious advance signals. This makes prediction based on animal behavior extremely difficult, prone to both false alarms and missed warnings. Yet, the phenomenon persists. In 1989, residents of Northern California reported unusual animal behavior before the Loma Prieta earthquake. Dogs were said to be barking more than usual, cats hiding, birds leaving the area. A geologist named Jim Birkland famously predicted the earthquake by, among other methods, tracking missing pet ads in local newspapers. His theory was that more pets went missing before earthquakes because they were fleeing the area or behaving erratically enough that they got lost. After the earthquake, when his prediction proved accurate, he became something of a celebrity. But scientists remain skeptical of his methods, pointing out that he also made predictions that failed to come true, predictions that are conveniently forgotten when we remember only the successes. This is the problem of confirmation bias. We remember the hits and forget the misses. If your dog barks frantically one night and an earthquake occurs, you remember it. If your dog barks frantically and nothing happens, you forget it. Dogs bark for many reasons: threats, excitement, boredom, sounds we cannot hear, animals moving in the distance. Most of this barking has nothing to do with earthquakes. But after an earthquake, the mind naturally searches for patterns, for signs that might have predicted the event. In hindsight, normal behavior can seem ominous. The cat that hid under the bed, something it does occasionally anyway, becomes a precursor signal. The birds that seemed quieter than usual, perhaps they were, perhaps you simply weren't paying attention on other days, become a warning sign. This doesn't mean animal detection is impossible, or that all reports are false. It means we have to be very careful about how we interpret observations, especially retrospective ones. This is why the Max Planck study is so valuable. By monitoring animals continuously and recording their behavior before researchers knew an earthquake would occur. The study avoided the pitfall of retrospective interpretation. The patterns in the data emerged without anyone looking for them beforehand. This is the gold standard for scientific evidence: objective measurement, independent of human expectations. Still, even with rigorous studies, the question of mechanism remains open. What exactly are the animals detecting? The answer might be different for different animals and different earthquakes. Dogs might detect one set of signals with their noses and ears. Elephants might detect another set with their feet and their infrasonic hearing. Birds might sense yet another set with their balance organs and magnetic receptors. And all of these might depend on the specific geology of the region, the depth of the earthquake, the type of rock, the presence or absence of groundwater, factors that vary from place to place and event to event. What we can say with increasing confidence is that the phenomenon is real. Animals do behave unusually before at least some earthquakes. The behavior begins well before humans can detect anything wrong. The behavior patterns are consistent enough that they can be measured objectively with modern sensors. What we cannot yet say is whether this knowledge can be turned into a practical prediction system. The challenges are immense. Animals produce a lot of what might be called false positives. They act strangely for many reasons that have nothing to do with earthquakes. Distinguishing earthquake precursors from normal variations in behavior would require continuous monitoring of large numbers of animals across wide geographic areas. Even then, the predictions would likely be probabilistic. Something might happen in the next day or two, rather than deterministic. An earthquake will strike at this time and place with this magnitude. But the pursuit of understanding continues. New technologies allow us to track animal behavior at scales and resolutions that were impossible even a decade ago. GPS collars, accelerometers, even implantable sensors that can measure an animal's stress hormones in real time. As these tools become cheaper and more widespread, we gather more data, slowly building a picture of what animals know and how they know it. The answers won't come quickly. Good science rarely does. But piece by piece, observation by observation, we move closer to understanding this ancient mystery, the mystery of how animals read the earth. And now, having explored what happens in those crucial seconds and hours before an earthquake strikes, let's turn our attention to specific animals, the creatures that have been caught in the act, so to speak, of detecting seismic activity. Let's examine what each species might be sensing and how their unique biology shapes their response. When most people think about animals detecting earthquakes, they think first of dogs. This makes sense. Dogs are our companions, living in our homes, sharing our lives in intimate ways that wild animals do not. When a dog behaves strangely, we notice. When that strange behavior coincides with an earthquake, even if the dog's behavior was only seconds ahead of what we felt, it leaves an impression. Dogs barking at nothing, dogs pacing and whining, dogs refusing to enter buildings, or insisting on being let outside. These are the stories that circulate after every major earthquake. The question is whether these anecdotal observations reflect genuine detection ability, or simply our tendency to find patterns where none exist. The evidence suggests it's a bit of both. Dogs almost certainly can detect P waves before humans can. This isn't particularly mysterious. Dogs have more sensitive hearing than humans, capable of detecting frequencies up to 60,000 Hz, compared to our upper limit of about 20,000 Hz. More importantly, dogs are physically closer to the ground than we typically are. When they lie down, their entire body is in contact with the floor or earth, creating multiple points of vibrational input. Their vestibular system, the organ responsible for balance and spatial orientation, receives information not just from the inner ear, but also from proprioceptors throughout the body, sensors in muscles and joints that detect position and movement. All of this creates a multifaceted system for detecting ground vibrations that is likely more sensitive than a human's, especially a human who is standing upright and relatively insulated from the ground by shoes and floors. But beyond P-wave detection, which gives only seconds of warning, do dogs sense longer-term precursors? The answer remains unclear. There are countless stories of dogs acting strangely hours or even days before earthquakes. They pace, they whine, they seem anxious for no reason. Sometimes they refuse to go into their regular sleeping areas, as if those places have suddenly become dangerous. In some accounts, dogs have reportedly refused to enter buildings that later collapsed in the earthquake, suggesting they somehow sensed structural weakness or instability. After the fact, these behaviors seem prescient, but absent rigorous measurement and controlled conditions, it's impossible to know whether they represent genuine detection or the normal variation in dog behavior that we reinterpret after an earthquake occurs. Cats present a similar picture. Lots of anecdotal reports, but limited hard evidence. Cat owners report cats hiding before earthquakes, seeking shelter in closets or under furniture. They report cats becoming agitated, meowing urgently, or acting frightened without apparent cause. Some report cats refusing to sleep in their usual spots, or attempting to leave the house. Again, all of this could represent genuine precursor detection, or it could represent normal cat behavior that takes on retrospective significance. Cats are, after all, creatures of habit who also have unpredictable moods. They hide sometimes. They meow urgently sometimes, usually because they want food or attention. Distinguishing earthquake precursors from normal feline fickleness is no simple task. One interesting difference between cats and dogs concerns static electricity. Before thunderstorms, and possibly before earthquakes, the electrical properties of the air can change. Static electricity builds up, creating the familiar phenomenon where touching a metal doorknob produces a shock. Cats, with their fine fur, are particularly sensitive to static electricity. Their fur can stand on end when the air is charged, creating visible discomfort. This has led some researchers to speculate that cats might detect electrical changes associated with earthquake precursors, though this remains speculative. Dogs, especially short-haired breeds, seem less bothered by static, though they too can detect it. Moving beyond household pets, farm animals present some of the most compelling evidence for earthquake detection. This is partly because farm animals live outside, in constant contact with the ground, drinking from natural water sources, exposed to whatever gases or particles rise from the earth. It's also because farmers are extremely attentive to their animals' behavior. When animals represent your livelihood, you learn to notice when something is off. Farmers can tell at a glance whether cattle are stressed, whether horses are nervous, whether chickens are frightened. This makes their observations potentially more reliable than casual pet owners' reports. Cows, sheep, and horses have all been observed behaving unusually before earthquakes. In the Max Planck study mentioned earlier, the cows showed increased movement in the hours before seismic events. In the field, farmers report cattle becoming agitated, moving to different parts of their pasture, calling out more than usual. Sheep flock together more tightly, showing the kind of bunching behavior they display when a predator is near. Horses refuse to be led into stables, plant their feet, and resist, even when it's feeding time. None of this proves that farm animals can predict earthquakes days in advance, but it does suggest they detect something unusual in the period before shaking begins. The mechanism for farm animal detection might be similar to dogs and cats. P-wave sensitivity combined with whatever longer-term precursors exist. But there's an additional possibility. Farm animals spend much of their time with their heads down, grazing. Cows and sheep have their noses essentially pressed to the ground for hours each day. Horses, while not as low, still spend considerable time with their muzzles near the Earth's surface. This creates opportunities to detect gases or odors rising from the ground, particularly if earthquake precursors involve the release of volatile compounds. The olfactory systems of these animals, while perhaps not as acute as a dog's, are still far more sensitive than a human's. They can detect chemical changes we would miss entirely. There's also the question of herd behavior and social learning. Farm animals are herd species with complex social structures. When one animal becomes anxious, that anxiety can spread through the group rapidly. If even a few sensitive individuals detect something wrong, their behavior can trigger a herd-wide response. This amplification effect could make the precursor signal more obvious, turning individual detection into collective behavior that's hard to miss. From an evolutionary perspective, this makes sense. In nature, if several members of your herd suddenly act frightened, the smart response is to get frightened too, even if you didn't detect the danger yourself. Better to run with the herd for no reason than to stay put and get eaten. Chickens and other birds present another fascinating case. Multiple reports document chickens refusing to go into their coops before earthquakes, even at dusk when they would normally roost. Some reports describe chickens flying into trees, behavior that's unusual for breeds that have been domesticated for generations and have largely lost their ability to fly properly. Other reports mention chickens stopping their egg-laying or becoming aggressive when handled. Birds in general have excellent balance systems. Their lives depend on it. Flying requires exquisite control of three-dimensional motion. The structures in their inner ears are more sophisticated than most mammals. If earthquake precursors involve ground tilt or vibration, birds would be well equipped to detect them. But birds have another sensory system that might be relevant. Birds can detect magnetic fields. This ability is well documented for migratory species that navigate using magnetic information. The mechanism involves magnetite crystals in their beaks or iron compounds in their retinas, though the details are still being worked out. If earthquake precursors include disturbances to the local magnetic field, as some researchers propose, birds might detect these changes. This could explain why even non-migratory birds like chickens might sense something wrong before an earthquake. Then there are the reptiles and amphibians, snakes and toads and salamanders. The Haiqing earthquake was preceded by snakes emerging from hibernation in midwinter. Similar reports exist from other earthquakes. In 2009, researchers in Italy documented common toads abandoning their breeding pond days before a major earthquake struck. The pond was in a pristine natural area, far from roads or human disturbance, and toads had been breeding there reliably for years. Yet several days before the earthquake, they left, every single one, even though it was the peak of breeding season and the males had already established territories. They returned after the earthquake passed. The researchers, who happened to be studying the toads for unrelated reasons, were baffled. They could think of no explanation for the mass departure except the earthquake, though they couldn't prove causation. Reptiles and amphibians might be particularly sensitive to earthquake precursors because they live in such intimate contact with the ground. Snakes feel vibrations through their entire body. They can detect the footsteps of prey or predators from meters away. A toad's belly is pressed against the earth as it sits. Salamanders burrow into soil. All of this creates opportunities for detecting subtle changes in vibration, temperature, humidity, or chemistry that might precede an earthquake. These animals also have extremely slow metabolisms compared to mammals. They can survive conditions that would kill a dog or human, which means they're exposed to the environment in different ways, potentially picking up on signals that warm-blooded animals would avoid or not encounter. But perhaps no animal has captured scientific attention regarding earthquake detection quite like the elephant. Elephants are special for several reasons. First, they're intelligent, with complex social structures and behaviors that can be studied and documented. Second, they live in earthquake-prone regions of Africa and Asia, creating evolutionary pressure for earthquake detection, if such detection is possible. Third, and most importantly, elephants have sensory abilities that are well understood and that could plausibly detect earthquake precursors. Elephants communicate using infrasound, sounds with frequencies below the threshold of human hearing, typically below 20 Hz. These sounds can travel for kilometers through air and even farther through the ground. Elephants produce infrasound through their vocal cords, and they detect it through their ears and through their feet. The elephant's foot contains a thick pad of fatty tissue laced with mechanoreceptors, vibration sensors that pick up ground tremors. When an infrasonic wave travels through the earth, it creates subtle vibrations that propagate much farther than audible sound. Elephants can detect these vibrations, allowing them to communicate with other elephants many kilometers away and to sense the movement of other large animals or even vehicles from great distances. This same ability could, in principle, detect earthquake precursors. P waves, after all, are just vibrations traveling through rock. So are any other seismic signals. An elephant standing on the ground, with those sensitive footpads pressed against the earth, might be like a living seismograph. Some researchers have proposed that elephants could detect foreshocks, small earthquakes that sometimes precede larger events. Humans need instruments to notice foreshocks, but elephants might feel them directly. The most dramatic example of elephants possibly detecting seismic events comes from the 2004 Indian Ocean tsunami. This disaster was triggered by a massive magnitude 9.1 earthquake off the coast of Sumatra. The earthquake itself was devastating to nearby islands, but the real destruction came from the tsunami waves that followed, walls of water that swept across the Indian Ocean, killing more than 230,000 people in 14 countries. It remains one of the deadliest natural disasters in recorded history. In the aftermath, researchers and journalists investigated reports of animal behavior before the tsunami struck. What they found was remarkable. In Sri Lanka's Yala National Park, a wildlife reserve near the coast, officials reported that no large animals died in the tsunami, despite the fact that the waves swept several kilometers inland, covering parts of the park. 60 tourists died at the park's beach, but park rangers found no dead elephants, no dead leopards, no dead deer. The animals had apparently moved to higher ground before the waves arrived. Other reports came from Thailand, from India, from Indonesia. Elephants reportedly pulled up their stakes and fled inland, even breaking chains to do so. Dogs refused to go for their morning walks on the beach. Flamingos at a coastal sanctuary in India flew to higher ground. Buffalo on beaches lifted their heads, turned, and stampeded up hillsides, with bewildered villagers following and thus being saved. These stories are anecdotal, and some skepticism is warranted. In the chaos after such a disaster, distinguishing genuine reports from folklore and misremembering is difficult. But the pattern is striking. The reports come from multiple countries, from people with no contact with each other, describing similar behaviors. It seems unlikely that all of them are fabrication or error. Something happened that caused animals to flee before the tsunami arrived. The question is, what did they detect? The tsunami itself was generated by the earthquake. The earthquake produced seismic waves that traveled through the earth much faster than the tsunami traveled through water. P waves from the earthquake would have reached Thailand and Sri Lanka minutes before the tsunami waves. But the time gap reported in many accounts is longer than that. Elephants fleeing hours before the waves struck. Flamingos leaving the coast well before the earthquake occurred. This suggests that animals detected not the earthquake itself, but some precursor to it. Or they detected the earthquake, but interpreted it as a warning sign of danger that would arrive later. One hypothesis involves Rayleigh waves. These are a type of surface wave generated by earthquakes. Unlike P waves and S waves, which travel through the body of the Earth, Rayleigh waves travel along the surface, creating a rolling motion like waves on the ocean. They travel more slowly than P waves, but much faster than a tsunami propagates through water. Rayleigh waves from the Sumatra earthquake would have reached coastlines around the Indian Ocean well before the tsunami did. These waves are too subtle for most humans to notice without instruments, but elephants, with their ground-sensing feet, might have felt them clearly. Moreover, the vibrations would have had an unusual quality, different from normal background seismic noise, possibly alarming enough to trigger a flight response. There's also the possibility that elephants detected infrasound generated by the tsunami itself as it propagated across the ocean. Large waves create low-frequency pressure waves in the atmosphere. These infrasonic signals can travel hundreds of kilometers and arrive before the visible wave. Some researchers have proposed that elephants heard or felt these signals and recognized them as dangerous, even without having personal experience of tsunamis. This is speculative, but not impossible. Infrasound from large ocean waves is a normal part of the coastal environment. Elephants living near the coast would be familiar with it. The infrasound from tsunami waves is fundamentally different, much more intense, coming from an unusual direction, possibly creating a pattern that instinctively triggered a danger response. A researcher named Michael Garstang has studied elephant responses to environmental signals extensively. He proposes that the elephants in Thailand detected multiple signals. The infrasound of the actual tsunami waves striking the coast of Sumatra hundreds of kilometers away, transmitted through both air and ground. The unusual sound of water receding along the local coastline as the sea pulled back before the tsunami arrived, and the strange smell of the exposed seabed, which is normally underwater. He suggests that elephants integrated all these unusual sensory inputs, recognized something was profoundly wrong, and fled inland. This explanation relies not on any single superhuman sense, but on the elephant's ability to process complex multisensory information and respond appropriately to patterns that indicate danger. Whether any of these hypotheses is correct, we don't know for certain. What we do know is that the tsunami and earthquake provided a natural experiment, a rare event that tested animal detection abilities under real-world conditions. And the animals, particularly large mammals like elephants, appeared to perform remarkably well. They survived when humans, who had access to all of modern science and technology, did not receive adequate warning. This doesn't mean we should rely on elephants for tsunami prediction. It means we should study what the elephants know and learn to detect the same signals. The earthquake story is fascinating, but it's only part of the larger picture of how animals detect environmental changes. Earthquakes are sudden, violent, and relatively rare, at least large ones that cause obvious damage. Storms, on the other hand, are frequent and follow predictable patterns. Every region of the Earth experiences weather, and most regions experience storms, thunderstorms, hurricanes, typhoons, blizzards. The ability to detect approaching storms and prepare accordingly is hugely valuable for survival. It stands to reason that natural selection would strongly favor animals that can sense incoming weather changes. The evidence suggests that many animals can, and the mechanisms are in some ways better understood than earthquake detection. The key to understanding how animals detect storms lies in understanding a concept that's fundamental to meteorology but unfamiliar to most people: barometric pressure, also called atmospheric pressure. This is simply the weight of the air above you, pushing down on everything at the Earth's surface. At sea level, the air pressure averages about 1,013 millibars, or 14.7 pounds per square inch. This is a substantial amount of pressure, the equivalent of having a car sitting on a square foot of ground. We don't notice it because the pressure is equal in all directions, and our bodies are adapted to it. But the pressure isn't constant. It varies with altitude. Higher ground has lower pressure because there's less air above it. It also varies with weather. When a storm approaches, the pressure typically falls. When clear weather arrives, the pressure rises. These pressure changes are what barometers measure, and they've been used for weather prediction since the 17th century. Sailors learned to read barometers. A falling barometer meant a storm was approaching, time to secure the rigging and prepare for rough seas. A rising barometer meant improving weather. The correlation isn't perfect. Weather is complex and depends on many factors beyond pressure alone, but it's reliable enough to be useful. Modern weather forecasting still relies heavily on pressure measurements, though today we use sophisticated models and satellite data in addition to barometric readings. But here's what's remarkable. Long before humans invented barometers, animals were responding to pressure changes. They had to. A storm means danger. It means flying becomes difficult or impossible for birds. It means finding shelter is urgent for small mammals that can be killed by exposure. It means rough seas for marine life. An animal that can detect a pressure drop and respond by finding shelter before the storm arrives has a survival advantage over an animal that waits until the rain starts falling and the wind starts howling. Over evolutionary time, this advantage would be strongly selected for, leading to the development of pressure-sensing organs and pressure-responsive behaviors. The evidence that animals can detect pressure changes is now overwhelming. It comes from both field observations and controlled laboratory experiments. In the lab, researchers can manipulate air pressure independently of other weather variables, temperature, humidity, light, and observe how animals respond. These experiments have been conducted on multiple species, and the results consistently show that animals alter their behavior when pressure changes, even when they can't see, smell, or otherwise detect any other aspect of a storm. One of the most thorough studies was conducted at Western University's Advanced Facility for Avian Research. Researchers there have a hyperbaric climatic wind tunnel, a chamber where they can precisely control air pressure, temperature, and other environmental variables while birds fly or rest inside. Using this facility, they studied white-crowned sparrows, a common North American songbird. The researchers simulated winter storms by dropping the air pressure while keeping everything else constant. The response was immediate and dramatic. As soon as the pressure dropped, even before the lights came on to simulate dawn, the birds began eating voraciously. Normally, when birds wake up, they preen their feathers, hop around a bit, vocalize, and then gradually begin feeding. But when the pressure had been lowered overnight to simulate an approaching storm, the birds skipped all the usual morning activities and went straight to eating, as if they understood that the storm would make foraging difficult or impossible, and they needed to fuel up while they could. The researchers also simulated spring migration conditions, again manipulating pressure while controlling for other variables. When they raised the pressure to simulate the high pressure systems that bring clear weather and favorable winds for migration, the birds showed increased restlessness at night, the kind of behavior that precedes migratory flights. When they lowered the pressure to simulate an approaching storm, the birds remained calm, as if waiting for conditions to improve. The conclusion was clear. The birds were using barometric pressure as a cue to guide both short-term behavior, when to eat, and long-term decisions, like when to begin migration. Subsequent studies have confirmed that barometric pressure affects migration timing in wild birds. A large-scale analysis of songbird migration across North America used automated radio telemetry to track when individual birds departed from their wintering or breeding grounds. The researchers compared these departure times with weather data from a global weather model. What they found was striking. The probability of departure was strongly correlated with changes in atmospheric pressure over the previous 24 hours. Birds were more likely to depart on nights when pressure had been rising, which indicates that a high pressure system, and therefore fair weather, is moving in. They were much less likely to depart when pressure was falling, which indicates that storms are approaching. Wind, precipitation, and cloud cover also affected departure probability, but pressure was by far the strongest predictor, working consistently across multiple species, seasons, and locations. This makes profound sense from the bird's perspective. Migration is energetically expensive and physically demanding. Flying for hours or days without rest, crossing oceans or mountain ranges, depletes fat stores that took weeks to accumulate. Getting caught in a storm during migration can be deadly. Wind can blow birds off course. Rain can ground them in unsuitable habitat. Cold can cause hypothermia. For a small bird weighing less than an ounce, a severe thunderstorm is a life-threatening event. The ability to detect approaching storms before departing on migration, or even better, to time departure to coincide with favourable weather, is hugely valuable. Natural selection would strongly favour birds with acute pressure sensitivity, and over millions of years, that's exactly what has evolved. But how do birds detect pressure changes? The answer lies in a small organ in the bird's inner ear, called the paratympanic organ. This structure was first described in the early 1900s, but its function wasn't understood for decades. It's now thought to work as both a barometer and an altimeter, detecting changes in air pressure that result from either weather changes or altitude changes. The paratympanic organ contains mechanoreceptor cells, cells that respond to physical deformation, similar to the hair cells in the cochlea that detect sound. These cells are arranged in a structure that can sense the expansion or contraction of air-filled spaces in the skull as outside pressure changes. When air pressure drops, the air inside the bird's skull expands slightly, creating pressure on the mechanoreceptors. When pressure rises, the air contracts, changing the stimulus in the opposite direction. This gives the bird a continuous readout of pressure trends. The organ is sensitive enough to detect pressure changes that would occur with altitude changes of just a few meters, which is useful for maintaining stable flight altitude. But it's also sensitive enough to detect the larger pressure changes that accompany weather fronts, changes of several millibars over a few hours. The paratympanic organ isn't unique to birds. Similar structures exist in reptiles and were likely present in dinosaurs. This suggests that pressure sensitivity evolved early in the evolutionary lineage that led to modern birds, probably as an adaptation for flight. But mammals, which evolved from a different lineage, don't have paratympanic organs. They detect pressure changes through different mechanisms, primarily through the vestibular system in the inner ear, and possibly through mechanoreceptors in other parts of the body. Dogs and cats have been observed responding to pressure changes before storms. Pet owners report that their dogs become anxious or restless when a storm is approaching, hours before the rain begins. Some dogs hide, seeking shelter in closets or bathtubs. Others pace and pant, showing classic signs of stress. Cats similarly may hide or become more vocal, meowing insistently as if trying to warn their owners. These behaviours occur even when the sky is still clear and there are no obvious signs of the approaching storm, suggesting the animals are responding to pressure rather than to visible clouds or other cues. One interesting behaviour is dogs and cats seeking out bathtubs before storms. At first glance, this seems puzzling. Why would a bird's bathtub provide better shelter than anywhere else in the house? The answer might relate to static electricity. Before thunderstorms, the electrical properties of the atmosphere change. The air becomes charged with ions, and static electricity builds up on surfaces. This is why you sometimes get shocked when touching a doorknob on a dry day, or why your hair stands up in certain weather conditions. Animals with fur are particularly affected by static buildup. Their fur can trap the charge, creating an uncomfortable tingling sensation. Porcelain and ceramic, like those in bathtubs and sinks, are insulators that don't conduct electricity. By lying on these surfaces, animals can minimize the static sensation. This doesn't mean they're detecting the storm through static alone. The pressure change is likely the primary cue, but the static provides additional confirmation that something unusual is happening with the weather. The mechanism by which dogs and cats detect pressure isn't fully understood, but it likely involves multiple sensory systems. The vestibular system can detect pressure changes through their effect on the fluid in the inner ear. Mechanoreceptors in the skin and joints might also respond to pressure, though this is speculative. What's clear is that the animals do respond, and they respond early enough that their behavior can serve as a practical warning for their human companions. This leads to an interesting question. Could we use animal behavior as a weather prediction tool? The answer is, we already do, informally. Farmers have been watching animal behavior for centuries to predict weather. When cows lie down in the field, rain is coming. When birds fly low, a storm is near. When ants build up their mounds, bad weather is approaching. Some of these folk predictions are accurate, based on genuine animal responses to pressure or other meteorological cues. Others are likely coincidental or misinterpreted. But the general principle that animals respond to weather before humans notice it is sound. The challenge with using animals for formal weather prediction is the same challenge faced with earthquake prediction, distinguishing genuine responses from normal behavioral variation. Animals do many things. They lie down, they fly low, they act anxious. Most of the time, these behaviors have nothing to do with weather. A cow lies down because it's tired or because the grass is better there. Birds fly low because they're hunting insects that are flying low. A dog acts anxious because it heard a noise or because it wants attention. Only occasionally do these behaviors indicate an approaching storm. Telling the difference requires careful observation and ideally objective measurements. But for personal use, for a farmer deciding whether to bring livestock into shelter, or a pet owner preparing to comfort an anxious dog, watching animal behavior can provide useful information that complements weather forecasts. There's also the question of how far in advance animals can detect storms. Most of the evidence suggests it's a matter of hours, not days. Pressure begins to drop as a storm system approaches, but the drop accelerates in the final hours before the storm arrives. This is when animal behavior becomes most obviously affected. A dog might show mild restlessness 12 hours before a storm, but it's in the final 3 or 4 hours that the behavior becomes unmistakable. This aligns with the physics of storm systems. The most dramatic pressure changes occur near the storm itself, in the hours immediately preceding its arrival. Detecting a storm a day in advance would require sensing much more subtle pressure trends, which might be possible for some species, but is likely at the limits of even animal sensitivity. The exceptions are very large storm systems like hurricanes. Hurricanes cause pressure drops that are detectable over hundreds of kilometers, days before the storm makes landfall. This creates opportunities for animals to sense the approaching danger much earlier. And indeed, the evidence suggests they do. Let's turn our attention now to how animals respond to these monster storms. The hurricanes and typhoons that represent the most powerful weather events on Earth. Hurricanes are fascinating and terrifying phenomena. They form over warm tropical oceans when conditions are just right. Warm water providing energy. Light winds allowing the system to organize. The Earth's rotation providing the spin. Once formed, a hurricane is essentially a vast heat engine, converting the thermal energy of warm ocean water into kinetic energy of wind. The winds spiral inward toward the center, the eye where pressure is lowest. The stronger the hurricane, the lower the central pressure, and the higher the winds. A Category 5 hurricane, the strongest classification, has surface pressures below 900 millibars, more than 100 millibars lower than normal. This is a pressure difference you could feel even with human senses. Your ears might pop. You'd feel a strange heaviness or lightness. For animals with sensitive pressure detection, the approach of such a storm would be unmistakable. Marine animals face particular challenges during hurricanes. The surface of the ocean becomes chaotic, waves towering to heights of 50 or 60 feet, water churned and mixed to depths of 300 feet or more. Oxygen levels can change. Salinity can change as fresh rainwater mixes with seawater. The noise must be overwhelming. The roar of wind and waves. For animals that need to breathe air at the surface, like marine mammals and sea turtles, hurricanes can be deadly. The turbulent surface makes it difficult or impossible to breathe. For fish and other fully aquatic creatures, the turbulence can still be dangerous, battering them against rocks or reefs, stirring up sediment that clogs gills, pushing them into unsuitable habitats. The logical response is to leave, to evacuate, before the storm arrives. But how would marine animals know a hurricane is coming? They can't see the weather forecast. They can't even see clouds. They're underwater. Yet, multiple studies have documented marine animals, particularly sharks, responding to approaching hurricanes by moving to safer areas, typically deeper water where the turbulence is less. The timing of these movements suggests that animals are detecting the storm well before it arrives, sometimes days in advance. One of the first systematic studies of this phenomenon was conducted in 2001 at Florida's Mote Marine Laboratory. Researchers were tracking juvenile blacktip sharks in shallow coastal waters when Tropical Storm Gabrielle approached. The sharks, which had been fitted with acoustic transmitters, suddenly left their usual coastal habitat and moved offshore into deeper water. The exodus occurred when the storm was still far away, before winds or waves became severe. The researchers concluded that the sharks had detected the falling barometric pressure associated with the storm and responded by evacuating. Subsequent studies have confirmed this pattern for multiple shark species. During Hurricane Irma in 2017, researchers tracked various species of sharks in Florida waters. Bull sharks, hammerhead sharks, and nurse sharks all left shallow waters and moved to deeper areas before the hurricane struck. The timing varied by species and by how close the animals were to the storm's projected path, but the pattern was consistent. Interestingly, tiger sharks, which are larger and more robust than the other species, didn't evacuate. They remained in relatively shallow water even as the hurricane passed over. Researchers speculate this might be because tiger sharks are less vulnerable to storm turbulence, and because they're opportunistic feeders that can take advantage of the aftermath of a storm when injured or dead animals provide easy meals. The mechanism by which sharks detect pressure changes is thought to involve their lateral line system. This is a series of fluid-filled canals running along each side of the shark's body, opening to the exterior through small pores. The canals contain hair cells similar to those in the inner ear of mammals. When water pressure changes, even slightly, it causes fluid movement in the canals, which bends the hair cells and triggers nerve signals. The lateral line is primarily used for detecting water movements created by prey or predators, sensing vibrations and currents. But the same system that detects a struggling fish could also detect changes in water pressure associated with an approaching hurricane. There's also evidence that sharks might detect atmospheric pressure changes even though they're underwater. Water pressure increases with depth, but atmospheric pressure affects the surface, and pressure waves can propagate through water. A sufficiently sensitive pressure detector could pick up the changing atmospherics pressure even at depth. Additionally, changes in atmospheric pressure affect ocean currents and wave patterns, which sharks could detect through their lateral line. The exact mechanism probably involves multiple cues working together: pressure, wave patterns, changes in water chemistry, possibly even infrasound from the storm itself, traveling through the water. The behavior of sharks before hurricanes has practical implications. Researchers have proposed using sharks as living sensors, tracking their movements to gather data about ocean conditions in regions where traditional buoys and instruments are sparse. Sharks swim freely across vast areas, going places where it's difficult or expensive to maintain monitoring equipment. They're equipped with natural sensors for pressure, temperature, and currents. By attaching transmitters to sharks and tracking their movements, scientists could potentially improve hurricane prediction and ocean modeling. This isn't science fiction. Such programs are already in operation, providing valuable data that complements traditional meteorological observations. But sharks aren't the only marine animals that respond to storms. Dolphins and whales have been observed moving away from coastal areas before hurricanes strike. The mechanism here might be different from sharks. Marine mammals breathe air, so they're directly exposed to atmospheric pressure changes when they surface. They might detect falling pressure the same way terrestrial mammals do, through their vestibular systems and other mechanoreceptors. There's also evidence that dolphins and whales can detect changes in water salinity. Before a hurricane, heavy rainfall in the outer bands of the storm freshens the surface water, reducing its salt content. This creates a salinity gradient that cetaceans might detect, essentially tasting the approaching storm in the water around them. Marine mammals face an additional danger during hurricanes. They need to breathe, which means surfacing regularly. In calm seas, this is effortless. In hurricane seas, with waves reaching heights greater than the animal's body length and wind tearing spray from the wave crests, surfacing to breathe becomes hazardous. A dolphin or whale caught in the turbulent surface layer can inhale water instead of air, leading to drowning. This makes early detection and evacuation particularly important for these animals. Unlike sharks, which can simply dive deep and wait out the storm without needing to surface, marine mammals must continue breathing throughout. Moving to calmer waters, either offshore where the water is deeper and wave energy is less concentrated, or into protected bays if such refuges exist, can be a matter of survival. Sea turtles face similar challenges. They breathe air but spend most of their time underwater. During hurricanes, hatchling and juvenile turtles, which are small and weak swimmers, are particularly vulnerable. Adult turtles can dive deep to avoid surface turbulence, and some species can remain submerged for hours while resting, reducing their need to surface during the worst of the storm. But eventually, they must breathe, and timing that breath during hurricane seas is dangerous. Reports from hurricane-affected areas sometimes describe sea turtles being thrown onto beaches by storm waves, stranded high on the shore, or injured by being battered against rocks and reefs. Those that successfully detect the approaching storm and evacuate to safer waters survive. Those that fail to detect it, or that cannot leave in time, suffer or perish. Even creatures as small as fish respond to pressure changes. During storms, particularly hurricanes, fish often move to deeper water or seek shelter in caves, crevices, or behind reefs. This behavior has been observed by divers and documented through underwater monitoring. The mechanism is likely similar to sharks, detection through lateral line organs. But fish face an additional challenge related to pressure. Most bony fish have a swim bladder, an air-filled organ that provides buoyancy. The swim bladder is like an internal balloon. As pressure changes, the bladder expands or contracts. During a hurricane, if fish are forced upward toward the surface by turbulent currents, the decreasing pressure causes their swim bladders to expand. If the expansion is too rapid or too great, it can cause barotrauma, physical injury from pressure changes. The swim bladder can burst, or it can expand so much that the fish becomes too buoyant to swim downward again, forcing it to float helplessly at the surface where storm waves can batter it. Some fish have been found dead or dying on beaches after hurricanes, victims of barotrauma. Those that detect the storm early and move to stable depths avoid this fate. Birds also respond to hurricanes in fascinating ways. Unlike marine animals, birds have the option to simply fly away from the storm, and many do. In the days before a hurricane makes landfall, radar systems often detect large numbers of birds leaving coastal areas and moving inland. The birds are responding to the pressure drop, the same cue they use to time migration, but in this case, using it to flee a storm. Smaller birds face particular risks from hurricanes. Their light bodies are easily blown off course by strong winds. Getting caught in the eye wall of a hurricane, where winds exceed 100 miles per hour, can be fatal. Birds can be blown out over the ocean and drowned. They can be thrown against buildings or trees. The smart strategy is to leave before the storm arrives. But not all birds evacuate. Some, particularly seabirds, actually fly into hurricanes. This might seem insane, but there's logic to it. The eye of a hurricane, the calm center, is a refuge. Inside the eye, winds are light, the air is clear, and birds can fly normally. By flying into the storm and staying in the eye, birds can avoid the worst of the winds. Radar images from hurricanes have detected large numbers of birds in the eye, circling as the storm moves, essentially riding along inside the calm center. When the storm makes landfall and weakens, the birds can exit and return to normal foraging. This strategy works for strong, experienced flyers like frigate birds or pelicans. For smaller songbirds, attempting it would be suicidal. They lack the stamina and strength to fight their way into the eye against hurricane-force winds. Some birds caught by hurricanes end up in unexpected places. If a storm changes direction or moves faster than expected, birds that were evacuating ahead of it can find themselves caught in the winds and blown hundreds or even thousands of kilometers off course. After Hurricane Wilma in 2005, rare tropical birds were spotted in North America, far outside their normal range, blown northward by the storm. After Hurricane Matthew in 2016, birds from the Caribbean were found in Europe, carried across the Atlantic by the storm's circulation. For these individuals, being caught in the hurricane likely meant death, exposure to cold climates they weren't adapted for, starvation in unfamiliar habitats, exhaustion from days of flight without rest. The birds that avoided this fate were those that detected the storm early enough and evacuated in time. The physiological stress that storms place on birds is significant. Even those that successfully evacuate experience disruption. Migration timing can be thrown off. Birds that intended to fly south in autumn might be forced to flee west or north to avoid a storm, using up energy and time that they needed for actual migration. Breeding can be disrupted. Nests can be destroyed. Eggs and chicks can be lost. For species already struggling with declining populations, hurricanes add additional pressure. But from an evolutionary perspective, these costs select for better storm detection. Birds that can sense storms earlier, that respond more appropriately, that make better decisions about whether to flee or shelter in place. Those are the individuals that survive to reproduce. Over generations, the population becomes increasingly sophisticated in its storm sensing abilities. And storms don't just affect birds directly, they affect the entire ecosystem. Hurricanes and severe storms alter landscapes, knock down trees, flood areas, change water chemistry, stir up sediments. These changes affect food availability, habitat quality, predator-prey relationships. Animals that can predict when storms will occur can prepare, eating extra food beforehand to build energy reserves, moving to safer locations, altering their activity schedules. Those that cannot predict miss opportunities to prepare and suffer accordingly. This brings us to a key point that applies to both earthquake and storm detection. The ability to sense environmental changes is valuable only if the animal can act on that information appropriately. An animal that detects a P wave seconds before an earthquake but doesn't know what the sensation means, or doesn't know how to respond, gains no benefit. The detection must be coupled with an appropriate behavioral response. This means that earthquake and storm detection abilities must have evolved together with earthquake and storm avoidance behaviors. Natural selection shaped not just the sensory organs, but also the neural circuits that interpret the sensory information and trigger the flight response. This evolutionary perspective helps explain why animal detection of disasters isn't universal. Not all animals show unusual behavior before earthquakes. Not all birds flee before hurricanes. The ability exists, but it exists primarily in species and populations that have experienced disasters frequently enough for natural selection to favor the trait. An animal population in a seismically quiet region has no evolutionary reason to develop earthquake detection. A bird species that breeds in the Arctic, where hurricanes never occur, would have no use for hurricane detection abilities. The trait emerges where it's needed, shaped by the local environment and the local risks. But when the trait does exist, when an animal can detect environmental changes that signal approaching danger, the ability is remarkable. It represents millions of years of evolution, of countless individuals whose genes were tested against the harsh reality of natural disasters. Those that passed the test, that sensed and fled, survived to pass on their genes. Those that failed were eliminated. What we see today, the dog that barks before an earthquake, the elephant that flees before a tsunami, the shark that evacuates before a hurricane. These are the descendants of the survivors, carrying in their genes and in their nervous systems the accumulated wisdom of deep time. Now, having explored how various animals detect earthquakes and storms, let's delve deeper into one of the most remarkable detection mechanisms we've encountered: the ability to perceive infrasound. This low-frequency sound, below the threshold of human hearing, turns out to be one of nature's most important channels of information. For animals that can hear it, infrasound provides early warning of events occurring hundreds of kilometers away. It's a skill that humans can barely imagine, like having a sense organ for distant events, receiving information that our own senses cannot detect, and our instruments only recently learned to measure. Infrasound is defined as sound below 20 Hz, the lower limit of human hearing. But this definition is somewhat arbitrary. Humans can perceive infrasound if it's loud enough, feeling it as a pressure or vibration, rather than hearing it as sound. Stand next to a large speaker, playing a 15 Hz tone at high volume, and you won't hear a pitch, but you'll feel something in your chest, a physical sensation, like being pressed by an invisible hand. This happens because low-frequency sounds have long wavelengths. Wavelengths measured in meters or even tens of meters, which interact with objects of similar size, like the human body. The sound doesn't stimulate the ear's sound-detecting mechanisms, which are tuned for higher frequencies, but it does create whole-body vibrations that we can feel. For many animals, infrasound isn't a vibration to feel, but a sound to hear. Their auditory systems extend into frequencies below human range. Elephants can hear down to at least 14 Hz, probably lower. Whales can produce and detect infrasound well below 10 Hz. Even some birds may perceive very low frequencies, though the evidence here is less clear. For these animals, infrasound opens up a new world of information. It allows them to detect events at distances that would be impossible using higher frequency sound, because infrasound propagates much farther than higher frequency sound does. The reason infrasound travels so far relates to how sound propagates through air. All sound is absorbed to some extent as it travels. Energy is lost to friction with air molecules, to scattering by particles and obstacles, to being reflected and dispersed. Higher frequency sounds are absorbed more rapidly than lower frequency sounds. A 20,000 Hz sound might travel only a few hundred meters before becoming inaudible. A 200 Hz sound might travel several kilometers, but a 20 Hz sound can travel dozens of kilometers, and a 2 Hz sound can travel hundreds of kilometers under the right atmospheric conditions. This inverse relationship between frequency and propagation distance means that infrasound is ideal for long-range communication and for detecting distant events. Many natural phenomena produce infrasound. Avalanches create infrasonic signals as huge masses of snow roar down mountainsides. Volcanic eruptions generate infrasound through explosions and through the movement of magma and ash. Earthquakes produce infrasound through the shaking of the ground and structures. Ocean waves, particularly large storm waves, create infrasound continuously as they break. And crucially for our discussion, thunderstorms and hurricanes are prolific producers of infrasound. Thunderstorms generate infrasound through multiple mechanisms. Lightning itself creates infrasound. The sudden heating and expansion of air along the lightning channel sends out shockwaves at all frequencies, including infrasonic. Thunder, the rumbling sound we hear, is actually a mix of frequencies, from the low-frequency boom to the higher frequency crack. The lowest frequencies, below human hearing, propagate much farther than the audible thunder, meaning that the storm is making noise at distances far beyond where any human can hear it. Additionally, the turbulent air motions inside a thunderstorm, the powerful updrafts and downdrafts, the swirling winds, create infrasonic signals as huge volumes of air move rapidly. These signals are continuous as long as the storm exists, and they grow stronger as the storm intensifies. Hurricanes are even more powerful sources of infrasound. The enormous circulation of a hurricane, with winds spiraling around the center for hundreds of kilometers, creates infrasound at frequencies around 1 Hz or even lower. These signals can be detected by instruments thousands of kilometers away. In fact, global monitoring networks designed to detect nuclear explosions routinely pick up infrasound from large hurricanes, using it to track the storms and study their intensity. The hurricanes announce themselves to anyone or anything listening in the right frequency range, broadcasting their presence across vast distances. For elephants, this creates an extraordinary capability. An elephant standing in Namibia, in southern Africa, could theoretically hear a thunderstorm in Angola, more than 100 kilometers away. The elephant can't see the storm. The storm is beyond the horizon. But the infrasound from the storm's thunder travels through the atmosphere, carrying information about the storm's location and intensity. For elephants living in arid regions, where water is scarce and rains are infrequent, this ability is tremendously valuable. By detecting distant storms, elephants can navigate toward rain, traveling to areas where water will be replenished. Michael Garstang, a researcher who has studied elephant behavior and meteorology extensively, proposes exactly this scenario. He suggests that elephants in the extremely dry regions of Namibia use infrasound from distant thunderstorms to locate water during droughts. When the rains fail locally, elephants need to find areas where rain has fallen or is about to fall. By listening to the infrasonic signals from storms, they can detect rain events more than 100 kilometers away and begin traveling toward them. This navigation ability could explain the mysterious long-distance movements of elephant herds, movements that seem purposeful, but whose goal isn't always obvious to human observers. The mechanism by which elephants detect infrasound is twofold. They hear it through their ears, which contain specialized structures sensitive to low frequencies. The elephant's ear is large, which helps larger structures resonate at lower frequencies. But even more remarkably, elephants detect infrasound through their feet. This discovery, which came from playback experiments and biomechanical studies, reveals a completely non-intuitive sensory channel. When infrasound travels through the air, it causes tiny pressure fluctuations. When these fluctuations reach the ground, they cause the ground to vibrate very slightly. The vibrations are minuscule, far too small for humans to detect without instruments. But elephants have footpads containing a dense network of mechanoreceptors, cells that respond to pressure and vibration. These receptors are so sensitive that they can detect the ground vibrations created by infrasound, particularly when the elephant is standing still and paying attention. In experiments, researchers have played recorded elephant calls to wild elephants and observed their responses. When the calls are played through speakers in the air, elephants respond by listening, turning their ears toward the sound. but when low-frequency components of the calls are played through a speaker placed on the ground, transmitting the sound through the earth rather than the air, elephants respond differently. They freeze, becoming very still. They often lift one foot slightly off the ground, alternating feet, as if adjusting their stance to better detect the signal. Sometimes they press their trunks against the ground, adding another point of contact for vibration detection. This behavior suggests they're using their feet to listen, augmenting their aerial hearing with ground-based detection. This ability to hear through the ground explains otherwise puzzling aspects of elephant behavior. Elephants can detect other elephants from kilometers away, farther than sound should carry through air in their habitat. But if the signal is also being transmitted through the ground, as seismic vibrations, the detection range increases substantially. Seismic waves in solid earth travel much faster and farther than sound in air. An elephant's call, transmitted both through air and ground, creates two signals: an airborne one that arrives after several seconds, and a ground-borne one that arrives almost instantly. By analyzing the time difference and the characteristics of both signals, elephants might extract information about distance and direction that would be impossible from either signal alone. This same system that allows elephants to detect other elephants also allows them to detect distant storms. The infrasound from a storm travels through both air and ground. An elephant, sensitive to both channels, receives redundant information, confirming that the signal is real and not just noise. The intensity of the signal provides information about the storm's strength, the direction from which it arrives, determined by which feet or which ear detects it most strongly, provides information about where to go. It's a biological storm detection system of remarkable sophistication. But elephants aren't the only animals that use infrasound. Whales are perhaps even more impressive. Blue whales, fin whales, and other baleen whales produce calls at frequencies as low as 10 to 20 Hz, and they can detect infrasound at similar or even lower frequencies. The blue whale's call is the loudest sound produced by any animal, reaching sound levels of nearly 190 decibels. At such intensities, the calls can be detected by other whales over distances of hundreds or even thousands of kilometers. The ocean is an excellent medium for sound propagation, particularly at low frequencies where absorption is minimal. A blue whale calling in the South Atlantic could theoretically be heard by another blue whale in the Indian Ocean, on the other side of the African continent, with the sound traveling through deep ocean sound channels that guide and preserve the signal. Why do whales use infrasound? The answer relates to their lifestyle. Whales live in an enormous three-dimensional habitat where visual contact is often impossible. Water absorbs light rapidly, limiting visibility to tens of meters at most in clear water, and just a few meters in murky water. Smell doesn't work underwater, or rather, it works differently and isn't useful for detecting things at a distance. But sound works brilliantly in water, traveling much faster and farther than it does in air. By using low-frequency sound, whales maximize their communication range, allowing individuals to remain in contact across distances that would fragment a population into isolated groups if they relied on any other sense. Whales also use infrasound to navigate and to detect environmental features. The ocean isn't silent. It's filled with sounds: waves breaking, ice cracking, ships moving, earthquakes rumbling, volcanoes erupting, rain falling. Many of these sounds have infrasonic components. By listening to this ambient soundscape, whales can orient themselves, locating coastlines, underwater ridges, even temperature boundaries between water masses, all from the characteristic sounds these features produce or affect. This is speculative in some details. We can't ask whales what they hear or what they're listening for. But the capability is there. The ocean is full of infrasonic information, and whales have the sensory apparatus to detect it. Some researchers have proposed that whales might detect distant storms through infrasound, just as elephants might. Hurricanes and large storms generate intense infrasound that propagates through both air and water. A hurricane in the Caribbean creates infrasonic signals that could be detected by whales in the Gulf of Mexico or even the North Atlantic. Whether whales actually use this information to avoid storms is uncertain. Whales are large and robust, better equipped to weather storms than most animals. They can dive deep, avoiding surface turbulence entirely. But for whales that need to remain near the surface to feed, or for mothers with calves that cannot dive as deep, storm information could be valuable. At a minimum, detecting a storm might prompt whales to move to deeper water, or to postpone surface activities until the storm passes. Even animals that don't produce infrasound might still detect it. Pigeons have been shown to respond to infrasonic signals, and some researchers propose that pigeons use infrasound for navigation, detecting the distant sounds of breaking surf to locate coastlines, or the sounds of wind over mountain ranges to avoid bad weather. Other birds that migrate long distances might use similar cues. The evidence is suggestive, but not conclusive. Controlled experiments on bird hearing capabilities show that they can detect frequencies down to about 100 Hz, but whether they perceive true infrasound below 20 Hz is debated. What's clear is that birds alter their behavior in response to approaching storms, and at least part of that response is based on detecting barometric pressure changes, which we've already discussed. Whether infrasound provides additional information remains an open question. Crocodilians, alligators, and crocodiles, and their relatives, produce infrasound as part of their mating displays. Males create low-frequency vocalizations, roars combined with infrasonic components, that can be detected by females from considerable distances. The infrasound causes the water on the male's back to vibrate, creating visible waves on the surface, a phenomenon called the water dance. This display is dramatic, a blend of sound, vibration, and visual spectacle. But it also serves a long-distance communication function. The infrasonic components travel much farther through the swamp than the audible roars do, allowing females to locate calling males from greater distances. Presumably, the females can also hear or feel the infrasound produced by storms, though whether they use this information to alter their behavior isn't well documented. Tigers are another species reported to use infrasound. The tiger's roar contains frequencies below human hearing. When a tiger roars, people nearby might feel a strange sensation, a feeling of unease, or even mild nausea, even if they can't consciously hear anything. This is the infrasound, stimulating the body and nervous system in ways that don't involve the auditory cortex. The evolutionary function isn't entirely clear. It might serve to intimidate other tigers, establishing dominance or defending territory. It might serve to confuse or paralyze prey, taking advantage of the disorienting effect of infrasound on other animals. Or it might simply be a consequence of the tiger's large body size and vocal anatomy, producing low frequencies as a byproduct of being a large animal with large vocal folds. What all of these examples illustrate is that infrasound is a ubiquitous feature of the natural world, produced by countless sources and detected by diverse animals. For humans who cannot hear it, this creates a kind of sensory blind spot. We walk through an environment filled with infrasonic signals, completely unaware of their existence, except when we measure them with instruments. For animals that can hear infrasound, the world is richer, filled with information about distant events and environmental conditions that we cannot access. It's humbling to realize how much we're missing, how limited our sensory window is compared to other creatures. This raises a provocative question. If animals can detect infrasound from distant storms, earthquakes, and tsunamis, could we use their behavior to improve our own warning systems? Could we, in effect, outsource some of our monitoring to the natural world, using animals as distributed sensors? The idea isn't as far-fetched as it might sound. We already use animals for detection tasks. Dogs detect drugs and explosives. Rats have been trained to detect tuberculosis by smell. Dolphins have been used by militaries to locate underwater mines. In each case, the animal's superior sensory abilities are harnessed for human purposes. Could we do the same with earthquake and storm detection? The Max Planck researchers who studied farm animals in Italy envision exactly this. They propose creating networks of monitored animals in earthquake zones. Animals equipped with accelerometers or other sensors that continuously record behavior. The data would be analyzed in real time by computer algorithms looking for patterns that precede seismic events. When a sufficient number of animals in a region showed unusual activity, an alert would be issued, giving people time to take precautions. The system wouldn't replace traditional seismographs, but it would complement them, adding another layer of information. The challenges are significant. Animal behavior is noisy in the statistical sense. Animals do many things for many reasons. Distinguishing earthquake precursors from normal behavioral variation requires sophisticated analysis and large amounts of data. False alarms would be common, especially early in the program's development. There's also the question of scale. To provide useful coverage of an earthquake-prone region, you'd need thousands or tens of thousands of monitored animals. The cost and logistics of maintaining such a network would be substantial. And even if you overcame all these challenges, the warnings might provide only hours of advance notice, not days or weeks. For some applications, like automatically shutting down sensitive industrial equipment or pausing surgeries, hours might be sufficient. For evacuating entire cities, it's probably not. For storms, the situation is somewhat better. Hurricanes and large storms already provide days of warning through traditional meteorological methods. Animals might offer incremental improvements, detecting subtle features of storm development that instruments miss, or providing information in regions where monitoring infrastructure is sparse. But it's unclear whether the additional information would justify the cost and effort of monitoring animal behavior at scale. The primary value might be in research, using animals to help us understand which environmental signals precede storms and how those signals propagate. Once we understand what the animals are detecting, we can build instruments to detect the same things, potentially achieving better coverage and reliability than biological sensors can provide. There's also an ethical dimension. Using animals as sensors requires instrumenting them, attaching devices that might cause discomfort or alter their behavior. For wild animals, this raises questions about interference with natural behaviors and potential harm. For domestic animals, the burden is less since many already wear collars or tags. But there's still the question of whether their behavioral data should be used without the owner's explicit consent. These aren't insurmountable problems, but they need to be considered carefully as any animal-based warning system is developed. Perhaps the most valuable outcome of studying how animals detect earthquakes and storms isn't a practical prediction system, but rather a deeper appreciation for the capabilities of animal senses and a renewed humility about our own limitations. We live in an age of technological confidence, surrounded by instruments and tools that extend our senses in remarkable ways. We can detect gravitational waves from colliding black holes billions of light years away. We can sequence individual DNA molecules. We can image the interior of a living brain. Yet, a simple farm animal can detect an approaching earthquake hours before our seismographs notice anything unusual. An elephant can hear a storm 100 miles away, using senses we don't possess. A shark can navigate by magnetic fields we cannot feel. These are reminders that for all our cleverness, we remain limited by our biology, perceiving only a narrow slice of the information-rich world that surrounds us. What animals teach us is that the world is more connected than it seems. A thunderstorm in one country creates vibrations that propagate through the atmosphere and into the ground, detectable in another country. An earthquake building deep underground alters groundwater chemistry and electromagnetic fields at the surface. The approach of a hurricane changes pressure and wave patterns hundreds of kilometers ahead of the storm. These connections exist whether we perceive them or not. Animals perceive them because their survival has depended on it for millions of years. We're only beginning to measure them because we've only recently developed instruments sensitive enough. The study of animal detection abilities sits at the intersection of multiple disciplines: ethology, the study of animal behavior; geophysics, which examines earth processes; meteorology, which studies weather; and sensory biology, which investigates how organisms detect and process information. No single discipline alone can explain how animals know when disaster approaches. It requires integrating knowledge about what changes in the environment, how those changes propagate, what sensory organs exist to detect them, and how neural circuits process the information and trigger behavioral responses. This kind of integrative science is challenging, requiring researchers from different fields to communicate and collaborate. But it's also deeply rewarding. The answers that emerge are richer and more complete than any single approach could provide. What becomes clear from this integration is that animals aren't predicting the future in any mystical sense. They're not psychic. They don't have ESP. What they have is acute attention to the present moment, to subtle changes in their immediate environment that we overlook or cannot sense. The pressure is dropping right now. The ground is tilting right now. Gases are being released right now. These aren't predictions, but observations, extremely sensitive observations. What looks like prediction to us, the dog barking before we feel the earthquake, the elephant fleeing before the tsunami, is simply a faster and more accurate response to information that exists in the environment all along. This distinction matters because it shapes how we think about using this knowledge. We're not trying to harness some paranormal power. We're trying to understand what physical signals precede disasters and how they can be detected. This is a tractable scientific problem. It may be difficult, requiring decades of research and technological development, but it's not mysterious. The signals exist. They obey physical laws. They can be measured. Animals have evolved to measure them. With sufficient effort, we can learn to do the same. In the meantime, watching animals can provide useful information, especially in settings where people live closely with animals and have intimate knowledge of their normal behaviors. A farmer who has tended cattle for decades knows when they're acting strangely. A pet owner who lives with a dog for years can distinguish anxiety from excitement, genuine fear from play acting. When these experienced observers report unusual behavior coinciding with earthquakes or storms, their observations carry weight, not because animals have supernatural powers, but because the observers are skilled at reading subtle behavioral cues that the rest of us would miss. This brings us to another important point. The study of how animals detect disasters isn't just about disasters. It's about understanding animal senses more generally, about mapping the full range of ways that animals interact with their environment. Every discovery in this field sheds light on capabilities that exist all the time, not just before earthquakes or storms. Elephants don't only hear infrasound when storms approach, they hear it constantly, using it to communicate with other elephants, to monitor their environment, to navigate their world. The earthquake detection is a special case of a general ability. Sharks don't only detect pressure changes before hurricanes. They use their pressure sensors continuously to navigate, to detect prey, to maintain their position in the water column. Understanding how these senses work in extreme situations, like approaching disasters, helps us understand how they work in everyday situations, revealing the richness of animal sensory experiences. This leads naturally to a broader question that extends beyond the scope of our specific topics tonight. But that's worth touching on briefly. What else are animals detecting that we don't know about? What other channels of information exist in the natural world that we can't perceive and haven't yet thought to measure? The history of biology is filled with discoveries of unexpected sensory abilities. For a long time, scientists didn't believe that animals could detect magnetic fields. It seemed too unlikely, too exotic. But accumulating evidence forced a re-evaluation, and now magnetoreception is accepted as a genuine sense, possessed by dozens of species. Infrasound hearing was similarly doubted until recordings and playback experiments proved its existence. Even the lateral line system in fish, which is now well understood and appears in every biology textbook, was once controversial. This suggests that our current understanding of animal senses is incomplete. There are likely capabilities we haven't discovered yet, either because we haven't looked for them or because we don't yet have instruments sensitive enough to measure the relevant stimuli. As technology advances, as we develop new ways to monitor the environment and new ways to observe animal behavior, we'll probably continue to be surprised. Each new discovery will force us to revise our mental model of what it's like to be an animal, to inhabit a different perceptual world than our own. That's part of what makes this field so compelling. We're not just solving a puzzle about earthquake and storm prediction. We're gradually reconstructing the subjective experience of other species, trying to understand what the world looks like, sounds like, feels like to a dog. an elephant, a shark, a bird. We'll never fully succeed because we can never truly inhabit another creature's consciousness. But we can come closer, building better models, designing better experiments, collecting more data, slowly peeling back the layers of mystery that separate us from our fellow inhabitants of this planet. This endeavor requires a particular kind of mindset, a blend of rigorous skepticism and openness to the unexpected. Skepticism is necessary because animal behavior is complex and easily misinterpreted. Humans are pattern-seeking creatures, prone to seeing connections that don't exist, especially in hindsight after dramatic events. Scientists studying animal detection must guard against these biases, designing experiments that control for confounding variables and testing hypotheses in ways that could definitively prove them wrong. This rigor is what separates science from folklore, data from anecdote. But skepticism alone isn't enough. Openness is equally important. When an experienced farmer insists that his cattle always act strangely before earthquakes, it's tempting to dismiss the claim as superstition. But what if he's right? What if he's detecting a real pattern that he can't explain, but that could be validated with proper measurement? A good scientist takes such claims seriously enough to investigate while remaining skeptical enough to demand evidence. This balance, respecting traditional knowledge while insisting on empirical verification, is how science progresses. Many of the best scientific discoveries have come from taking seriously something that seemed implausible at first. In the case of animals detecting earthquakes and storms, we're in a middle state. We have enough evidence to say that something real is happening, that animals do respond to approaching disasters in ways that suggest they're detecting precursor signals. But we don't yet have complete explanations. We don't know exactly what all the signals are, or exactly how all the animals detect them. We have pieces of the puzzle, some well established, like P-wave detection and barometric pressure sensitivity. Others, more speculative, like electromagnetic field changes and gas emissions. The complete picture will take time to emerge, probably decades of continued research. But the outline is already visible, and it's fascinating. What should we do with this knowledge in the meantime? For most people, the practical application is limited. If you live in an earthquake zone and your pet starts acting strangely, it might be worth noting, but it's not a reason to evacuate your house. Too many false alarms would result. If your dog barks frantically, and then, seconds later, you feel a tremor, you'll have confirmation that your pet detected the P wave, but the information comes too late to be actionable. For storm detection, animals might give you a few hours of advance warning, which could be useful in places without access to weather forecasts. But in most of the developed world, meteorological services provide far better information far earlier. The real value, at this stage, is in furthering our understanding. Researchers need to continue monitoring animals, recording their behavior, correlating it with environmental data, teasing apart the relationships between stimuli and response. This work is slow and painstaking, requiring patience and funding, and often producing more questions than answers. But it's work worth doing, not just for the potential practical benefits, though those would be welcome, but for what it reveals about the natural world and our place in it. We are the species that has built cities and civilizations, that has put footprints on the moon and probes at the edge of the solar system, that has decoded the human genome and imaged atoms. Yet, we are also the species that cannot feel the earth trembling until it's too late, that cannot hear the storm approaching until it's on top of us, that navigates by maps and instruments because we lack the innate sensory systems that guide other animals. This duality, powerful and limited, technologically advanced but biologically constrained, defines the human condition. Studying how animals detect disasters reminds us of the limitation side of that equation. It's a useful reminder, keeping us humble, keeping us curious, keeping us aware that there are modes of perception we can barely imagine. And that's where we'll leave this exploration tonight. Not with definitive answers to every question, but with a deeper appreciation for the questions themselves. How do animals know? What are they sensing? Can we learn to detect the same signals? These questions have occupied human minds for millennia, and will likely occupy them for millennia more. What's changed is that we now have tools to investigate rigorously, to move beyond anecdote and speculation toward understanding grounded in careful observation and measurement. The animals have always been there, sensing things we couldn't. We're only now learning to see what they've been seeing all along. So the next time your dog acts strangely, or you hear birds calling at an unusual hour, or you notice cattle bunched together when they should be spread out grazing, take a moment to wonder. What are they perceiving that you're not? What information is flowing through the environment, invisible to your senses, but clear to theirs? You might not have an answer, but asking the question, opening yourself to the possibility that there are things happening beyond your perception, that's the beginning of understanding. That's the mindset that leads to discovery. And sometimes, in the quiet moments when the world seems stable and predictable, it's worth remembering that beneath your feet, the earth is always moving, always changing, and somewhere an animal is paying attention. Thank you for joining me on Bedtime Biology tonight. If you enjoyed this deep dive into one of nature's most fascinating mysteries, please consider subscribing to the channel. Leave a comment below if you have thoughts to share, questions to ask, or suggestions for future topics. Your engagement helps these videos reach others who share your curiosity about the natural world. And if you've experienced unusual animal behavior before a natural disaster, I'd love to hear your story in the comments. Personal observations, combined with scientific study, help build our collective understanding of these phenomena. Until next time, sleep well, dream deeply, and remember that the world is far stranger and more wonderful than we usually imagine. The animals around us are connected to that strangeness in ways we're only beginning to understand. Good night.